Hello, everyone, and welcome to this AI Research Bytes session. My name is Marie-Lise, and I will be your host for today's session. This series of short and informative talks showcase cutting-edge research work from the AI ServiceNow research team. The AI Research Bytes are open to all, especially those interested in keeping up with the fast-paced AI research community. Today's session features a 15-minute talk from Massimo Caccia on LLM Web Agent, and the presentation will be followed by a 10-minute Q&A. Before we begin, let me share a few words about today's speaker. Massimo Caccia is a senior research scientist here at ServiceNow AI Research in the Frontier AI Research Program. He holds a PhD in deep learning from Mila, and his research focuses on computer use agents and reinforcement learning. With that, it's my pleasure to hand it over to our amazing speaker. Up to you, Massimo.
Thank you, Marie-Lise. Okay, so yes, today I will present some work on how to train your computer use agent. And this work was just accepted at NeurIPS, which is the top conference in AI research. So we're really excited about that. So in my team at ServiceNow, we focus on computer use agents. Okay, so this is quite simple. These are agents that can use a computer, but also can use maybe a mobile or web browser or even an IDE for coding. Yeah. So it's a really, really rich space of problems. There's a lot of things you can do. And that's why we're really excited about it. So, when you think about it, there is a lot of verticals in the economy that could kind of be automated with strong computer use agents. So, if you've played with ChatGPT before, you know that it's really intelligent. It can reason, but why can't it do mundane tasks that some, let's say, personal assistants have to do? Well, it's because ChatGPT cannot use a computer as well as them today. So we're really excited about this space of problem. And, because we are a lab that is within ServiceNow, we're going to focus on computer use agents that can actually do ServiceNow-like tasks. So in previous work, we created this benchmark, which is called Work Arena. It's basically an environment instantiated in the ServiceNow product where agents have to do ServiceNow-like tasks. So think about an AI agent that has to solve an IT ticket. So it needs to go in a knowledge base and troubleshoot the problem, then close the ticket. So those are really complex tasks that require a lot of steps. So the models are not great at them yet. People who are building agents within ServiceNow might already know that. So we're going to try to make them better. So the gist or the meat of the paper I'm presenting today is how can you get the best performing computer use agent at the lowest cost? Okay. And you can think about cost and compute interchangeably. Okay. Like the cost of running a smaller model versus a bigger model, as everything has to do with how much compute they require to be run. Okay. So we're going to first talk about the deployment of these models. So when you're going to deploy these agents, let's say you have a choice between a small model and a bigger, stronger model. Well, the bigger, stronger model is going to be better at the ServiceNow task, but it's also going to be much more expensive to run. And these models are going to run a lot of time, so you need to be smart about this cost. So we're going to make a first assumption that we're going to go with the smaller model, but we're going to try to get it as good or even better than the bigger model. Okay, we're going to try to get the best of both worlds. So now during training, we're starting with the smaller model, and we're going to make another assumption, which is that we have access to an environment of tasks that we can train this model in. Okay, so now we're going to ask the question, how should we spend our money or our compute to get this small model to become the best possible? So there's basically two ways we can go about this. The first strategy would be to do expert distillation. Okay, we're going to try to distill the knowledge of the bigger model into the smaller model. So how can we do this? We're going to take the bigger model and we're going to let it roam in the environment that we've built, doing the ServiceNow task. It's going to collect what we call episodes. Okay, so some episodes are going to be successful, some are going to be not successful. We're going to keep the successful episodes, and this is going to create a high quality data set that we can train the smaller model on. Okay, so this is strategy number one, expert distillation. The other strategy is to do reinforcement learning. So the only thing you need to know here is that in reinforcement learning, now the model who's collecting the data is the small model. So the small model is trying out by itself how to do the ServiceNow task. And when it gets it right, it will reinforce the behavior it did there. Okay, so these are the two approaches we can do. And fundamentally, the difference is who's collecting the data. So there's trade-offs between these two approaches. The first one is quite technical, which is that in reinforcement learning, the data is on policy, and in expert distillation, the data is off policy. To put it simply, let's say that you're trying to learn American football. Maybe the best way to go about this is not by trying to imitate what the pros are doing. You might just get injured, right? Your skill set is just so far from what the expert skill set is that it doesn't make sense to try to imitate them. So this is what we call off-policy bias. But another trade-off that is basically central in this work is the quality-quantity trade-off. So the smaller model, for the same amount of compute or for the same amount of money, is going to be able to collect more episodes than the expert. But those episodes are going to be of lower quality. Okay, to put some number on this, let's say that your smaller model, your student, has 10 billion parameters and your expert has 100 billion parameters. Well, for the cost of collecting one expert episode, you can collect 10 student episodes, but they're going to be of lower quality. So how do you want to spend your money between these two things is what we're going to try to answer. So the first thing we're going to do is a compute allocation study. We're going to compare expert distillation with reinforcement learning and with an hybrid approach between the two. Okay, and it's going to give us a really cool looking plot like this, which was quite popular when we put it on Twitter. Now, there's a lot to digest here, so I will try to walk you through it. So we're going to zoom in a little bit. And basically, the first star here represents the model, the student performance when it hasn't done any training yet. Okay. The second star is the model when it has done a bit of expert distillation, so a bit of imitating the expert. And then these orange curves represent branching off this model into reinforcement learning. So now the model is doing the thing on itself. Doing the thing itself. And so the x-axis is always compute or money, and the y-axis is the performance of the model. And what we can see here is that for whatever your compute budget is or your dollar budget is, the best way to spend it is always to do expert distillation first and then to do reinforcement learning. And it's a really robust finding because it's always the right way to spend your money. And this is rare that you see this in research. So we were really excited about that. So because it's always the best way to spend your money, it's also the way to get the best performance. So as you can see here, the performance of the student eventually outperforms the teacher and can also reach the performance of the closed source models, which is really exciting. So this is just one model in one benchmark, but in the paper, we've replicated this finding across two models, one American one Chinese one, and also on two benchmarks, and it just holds. So the takeaway of this experiment is that if you're building computer use agent, here's what you need to do. You will iteratively collect a bit of expert data and do some distillation. And then at some point, you will start to see the performance of your student flatlining. And this is when you want to go and branch off into reinforcement learning. So that's kind of the general recipe to get the best bang for your buck. So this is the main takeaway of the paper. But to get there, we needed to tame reinforcement learning. So if you've done reinforcement learning in the past, you know that it's extremely finicky. So you start a new problem, you have your new domain, you have your new model, you have your new algorithm, you start to try things and nothing works. And then you can iterate over weeks, you can iterate over months, and then at some point you try something slightly different, and then everything starts to magically work. So this is reinforcement learning, and then it gets even more complicated when you do reinforcement learning with models that have billions of parameters. So now, a billion things can go wrong. And also when you do these really long horizon complex work arena tasks, it gets even more brittle. So it took us months to nail that. And we thought we need to communicate to the community our findings here, our recipes. And so basically what we're going to try to explain now, we're going to get a bit more technical, is that we're going to try to find the optimal design choices for building these computer use agents. And we're also going to analyze, do these optimal design choices, do they change when you do different amount of expert distillation? Okay. So now we're going to get new sets of cool looking plots. And what these plots are showing us is basically in the first column will represent the model that has done no expert distillation. The middle column would be a bit of expert distillation. And then the last column would be a lot of expert distillation, okay? And here we're gonna analyze the first design choice, which is the discount rate, okay? So the discount rate is an important hyperparameter in reinforcement learning. It basically controls how much value you will put on trajectories depending on how long it takes the agent to do them, okay? So basically, if we take a step back, these agents, when they're doing reinforcement learning, they're always maximizing a reward. So if you put, let's say, a discount rate of 1, then doing an episode or solving a task in 1 minute versus solving a task in 10 minutes, that's going to be the same reward. So you're not really encouraging the model to be fast. But if you put that discount rate to a lower value, now doing a task in a minute versus 10 minutes, the 1 minute task is going to be of higher reward compared to doing it in 10 minutes. So it's a really brittle design choice, because if you put it too high, the model is going to be slow. And if you put it too low, now the model, nothing will be valuable. So the model won't learn anything. So let's analyze these design choices in our setup. So what we can see here is that if you start from the model that hasn't done any expert distillation, 80% of the time, a value of 0.9 is going to be the best value. That's quite reasonable in reinforcement learning. But if you do a lot of expert distillation, now things become quite interesting. The best discount rate will be 0.5, which is extremely aggressive. So our hypothesis here is that once the model knows a lot about the task or about the environment, now the best way to make it further improve is to be super aggressive with the discount rate to encourage it to do the task that it already knows in a quicker fashion. So we thought that was a really cool finding. Now I'm going to go really quick into some more technical findings that we saw. So if you're familiar with GRPO, we analyzed using the advantage function or not. We saw that if you start with no expert distillation, you don't want to use the advantage function, but later on you do. Similarly, some people have asked, do you want to normalize this advantage function with the standard deviation? At the beginning you want, but later you don't. And then maybe you want to use the importance ratio in your loss. At the beginning you don't, and then you do. So it's quite messy, but you need to know it if you're training computer use agents. And then in the paper, we have much more of these analysis for all the design choices we can think about. I will leave you with this little funny thing that happened when we ran our experiments. So we've built this work arena benchmark, and when agents are playing in it, they are allowed admin rights, okay? So something kind of funny happened. These agents, they would kind of cheat their way to success. So in a specific task, they would need to reach these task endpoints that can be hard to navigate to. So basically, some of them would just use their admin right to add this task endpoint in their own page so that they could directly go to it. So it would work, but it would kind of like break the spirit of the task. And also, it would break the environment for all the other agents because now their own page would be overcrowded with all of these random task endpoints. So we thought that was kind of funny and we removed those admin rights. So let's just do a quick recap. Today we saw that we studied how you want to spend your compute when you post-train these computer use agents. And we saw that a combination of expert distillation first and then reinforcement learning is how you want to spend your money. And then we look at some conclusion for design choices in reinforcement learning. And we saw that the level of expert distillation is going to change the optimal design choices. And that's pretty much it. This is the link to the paper. And also this is the link to the ServiceNow GitHub repos that we've used to do the experiments. So thanks for listening.